The first talk is going to be given by Nicholas Lane and Xinchi Chu. Nicholas Lane is an associate professor at the University of Cambridge, where he leads the Machine Learning Systems Lab. He's also a director at Samsung AI Center in Cambridge. Broadly, his research interests are on on-device and distributed forms of machine learning. Prior to Cambridge, he was an associate professor at Oxford and UCL. And among his awards, I'd like to highlight 2 ACM Test of Time awards, and more recently, ACM SIG Mobile Rockstar Award. This work is going to be presented as well by Xinchi Chu. She's a first-year PhD student at the Machine Learning System Lab in Cambridge. She has a background in mathematics, and yeah, she's one of the co-authors on the paper we're going to be hearing about right now.
Great, thanks Javier for the introduction. I just want to check, can you see the slides fine? Do they look fine?
Yeah, we can see them.
Perfect. Okay, well, so Xinchi and I want to speak to you today on behalf of all the folks that you see on this title slide. All of us have been very interested in the potential for federated learning to offer a more carbon-friendly machine learning solutions than we have today. And so this talk really has got 2 main parts to it. I want to share with you our aspirations for what federated learning might be able to offer us moving forward once a lot of research has been done into how we can best use it under this regime. And then that's more the aspirational part. There is also a technical core to this part that Xinchi will largely be telling you about. And that is a very exciting piece of work where we design and perform a lot of experiments that allow us, we think for the first time, to have a very good handle on the current carbon footprint of present-day federated learning methods as they relate to existing workloads that we see already. So with that, I've laid out where we're going to go in this talk. Let me say more about the motivation, why we are so interested in this issue of carbon footprint and environmental issues. And we all know that the environment is a pressing problem for the world generally. But what may not be paid enough attention in the world today is the role that machine learning is increasingly having in this environmental space. It doesn't matter what you do. So many of the things that we do on a daily basis now contain machine learning models being used at scale constantly. And so whether you're doing a web search and you're searching for a particular type of image, anytime you touch your phone and use it for some task, or if you just sit down on the couch and watch a bit of Netflix, what's not immediately obvious to you is that you are exercising hundreds of state-of-the-art models in all of these services. If you're searching for an image, we're using a variety of NLP and computer vision models to find the right result. If you're using your phone, there are literally hundreds of models being driven by apps in the system to provide its services. And Netflix itself has tens of models, if not more, to do a variety of personalization. Now, the issue is that machine learning is everywhere, and it has a surprisingly large carbon footprint. And so there's a recent analysis, or there's been lots of different studies, but just to take one piece of analysis, to train a bleeding edge state-of-the-art NLP model, it was observed that doing this centrally, that is to say, doing it in a data center, could easily produce as much carbon as 5 cars used for their entire lifetime. And so we're talking about significant amounts of pollution for training a single, granted a very state-of-the-art, but a single machine learning model. And so if you just think about the issue of data centers more broadly, that are being used today, they're the main workhorse, or the main place where we do all of this machine learning that we hear about in the news, and everything's being done in a data center today. Already, they contribute 0.3% of the carbon emissions, and this is growing by the day. It's growing because we're using machine learning not only in our consumer lives, which is the examples I gave before, but we're using it inside industry. More and more plants, when they produce items, they're using machine learning to make their decisions and drive the machinery. It's being used in business. It's being used in the stock market. Machine learning is just increasingly being adopted into all facets of our life. So that's one forcing function. The other forcing function that probably perhaps might alarm you is a figure that you've seen probably many times before, but I want to cast it in a new light. This is this piece of analysis that was done by OpenAI. It's on the y-axis, we're seeing log scale of the number of operations it takes to produce state-of-the-art machine learning models across the last, say, roughly 10 years. And what they find is that every 3 months, the compute need of the models are doubling. And so if you want to go from AlexNet to a few years later, VGG in 2015, to a few years later to these machine translation, and then more recently AlphaGo, if you plot the rate of travel and the rate of growth, there's a consistent doubling of compute every 3 months. It's a ginormous rate of increase. And this relates directly into the carbon output that we're thinking of that we're talking about today. Just imagine what is going to happen if we're going to look forward to future certain types of machine learning breakthroughs. The carbon footprint of data center based models is going to also increase roughly proportional to this amount of compute increased needs. So this is a serious problem that's only getting worse, and it touches every part of our life. So that's the motivation. That's why we're very curious about what federated learning can do. And let's talk a little bit about why we think there's a lot of potential. It's a decentralized approach where you can spread the load across many devices, many organizations, versus centralizing it all in one place. And so let me give you 3 anecdotal examples of why we think that federated learning may provide an important piece, not of course, not the full answer, but an important piece of how we move forward to build sustainable machine learning. Let me give you 3 examples. First example, in this decentralized approach, there's no need to cool. When you bring all of this compute together in one place, what happens is that you also need to cool it. And so typical data center PUE values run at 1.6. That means that 60% of the energy that's used by the data center is actually used for cooling. So cooling is a huge part of their energy and therefore carbon emission factors. Even very lean data centers by leading organizations like Google and Facebook and so on, they have PUE numbers that are much better, maybe around values of 1.16. But still, even for them, cooling is an appreciable value. And there's a large number of smaller data centers around the world. You'll find them used by universities, by smaller organizations that have much larger PUE and cooling needs. Second of all, and more fundamentally, it's well known within computer architecture, software design, and so on, that data movement has a ginormous amount of overhead in comparison to compute. So if I give you a computer architecture number, one memory operation uses memory operation, so moving a piece of data from one part of the computer to another, can actually use 1,000 times more energy than a single compute operation. Now, just think what happens when we have a decentralized approach to all of these machine learning problems, where the data can exist and stay on the edge, and yet you can still have the model trained, versus a situation where you need to move that data from the edge, from cameras across the world, from microphones across the world. If you need to move that data centrally and then compute on it, there's going to be severe data movement overhead from fundamentally that approach and building on top of it. And finally, if you look inside all these data centers and see how they're using their training, you're going to see an awful lot of redundant training being done, because individual organizations are always training very similar models for doing things like speech recognition, vision tasks, translation tasks. There's very little sharing going on between organizations. potentially federated learning could help alleviate this redundancy, enabling a situation where organizations train once or train very few number of times models that do the same thing and share those models. So these are the three avenues that we see that future versions of machine learning that are based on federated principles might have much better carbon footprints. And so before I hand over to Xinchi and she tells you about the real science here, again, where we think this might play out eventually, once a lot of research is done, is that perhaps federated learning can introduce and change the way we build sustainable systems moving forward. This slide, you can read these bullet points top down it's giving 4 different examples. So the most simplest example is that we think, actually in the near term, we can probably start to identify things that are being done in the data center today that would be more carbon efficient to do under a federated learning setting. So things like hotkey word recognition may be one of these things. Second, the way federated learning might be able to help in these environmental concerns is in helping develop hybrid approaches that uses some form of data center style approach combined with some lessons and some approaches borrowed from federated learning techniques. So you might see example where you have the data center begins to train the model, and then we have federated learning techniques used to finish off the model using data that's at the edge, and that might result in a model that's trained with a lower carbon footprint than simply training it all centrally. And finally, we'll talk about this at the end, we think there may be serious room to reinvent forms of machine learning moving forward, where you've built things in a much more decentralized fashion, and they might have far better carbon footprints than we currently have available to us. But let's now think about what we actually have achieved to date. And so Xinchi is about to introduce you to 2 pieces of work we performed in the last 12 months, which we're very excited by because it gives us a solid foundation, perhaps for the first time, to judge just how carbon emissions vary under various types of federated learning settings. We think this is a critical first step because it allows us to measure the current state of practice in federated learning and identify how it can improve to be more carbon efficient, and especially allow us for the first time to also compare it to different forms of centralized learning and understand when is it going to give us a win on the carbon footprint, when does it not, and what needs to change for us to change those types of comparisons. So with that, I'm going to hand over to Xinchi, who can tell you about the results that we have found.
Thanks, Nick. As Nick mentioned earlier, there are a lot of carbon potentials for federated learning. So we want to have a systematic way to estimate the carbon emission. There are some literatures estimating the carbon emissions for centralized learning, but here we will present the first to study about the carbon emissions for federated learning. We can summarize the estimation into 3 main steps as we show here in the graphs. If we go to the next slides, we can see that firstly, we need to estimate the total energy consumptions for training a model, either by centralized way or by federated learning way. To do that, we will firstly estimate the energy consumptions by the GPUs for data centers or CPUs for federated learning. We estimate the energy for training in a hardware by measuring the power consumptions during the training multiplied by the work clock time. For data centers specifically, as Nick mentioned earlier, we need to consider the actual energy for cooling and maintain the data center. To estimate this, we will use the PUE ratio, which is the power usage effective ratio, and which accounts for all the actual energy required for the data center, as Nick mentioned in the previous slides. For federated learning, as the training happens on the edge, there are no cooling required. Hence, we only estimate the training energy consumption by power assumptions by multiplied by the work clock time for the selected clients, and then sum up all the communications round. Last, for federated learning, during each round, the central server will broadcast the current model parameters to all the selected clients, and then clients will perform the local training and then send the updated model parameters back to the server. Therefore, communications is also a crucial part that we cannot omit. we estimate the communications by two parts. The first part is the download and upload consumptions by the routers, and the second part is the consumptions of the hardware when they are downloading and uploading. Here in the equations, part C, D stands for the download speed and U stands for the upload speed. And this speed can be dependent on the locations as well. And later, when we are doing the experiment, we will use the country-specific average speed for each estimation. And ER here stands for the router power, and idle stands for the hardware power when they are in the idle state. That is when they are downloading and uploading. If we go to the next slide, we can see that the second step is to estimate the carbon emission. After we estimate the total energy consumptions, we need to convert it to the carbon emission. It will be quite difficult to compute the exact amount of carbon emission in a given location. So we'll be using the reported conversion rate in each country. Here, the conversion rate means like an amount of carbon emission per kilowatt hour of the energy consumptions. As we expected, which these numbers are quite reliant on the carbon efficiency productions of each physical locations and countries. For example, France will have a very low carbon emissions carbon conversions rate, as France derives around 70% of its electricity from nuclear energy. And the final steps is to implement the federated learning using our framework, as you have already heard quite a lot during the previous talk. So in our paper, I will briefly go through the experiment setup. We will consider both the IID data partition and the non-IID data partition using the DOR data partition explained by the Petro earlier. And for centralized learning, we will be using one GPU, one V100 GPU per experiment, and we measure the exact power consumptions for each experiment. And for the federated learning, we will use two different devices to act our federated learning clients. And these devices one is TX2 and another one is Xavier NX, which can be quite see as the realistic pool of federated learning clients, as they can be found embedded in different IoT devices nowadays. For the completeness of the experiment, we conduct the experiment in 3 different kinds of data sets and in different kinds of model complexities. For the image data set, we use ResNet 18, and for the speech command and keyword spotting data set, we will use more lightweight stack of 4 layers of LSTM model. And also we consider different client pool. For the CFAR, we consider the 500 total of 500 clients and select 10 clients in each round. And for the ImageNet and speech command, we consider of 100 clients of the total client, and we also still only select 10 clients in each round. So in the next slide, to better show our slides, we will first start with a case study of the speech command dataset, which we can show that federated learning has the potential to be more carbon efficient than centralized learning. Speech command is a keyword spotting task, which we think is a very good representation of what kind of task we'll find it deploying on the edge device and be more likely to use federated learning. And also we use the lightweight STM model, which is quite realistic and practical as well. Comparing with centralized learning, we normally think that federated learning is slow to train and converge because it trained for following the communications round, and it needs more communications round than centralized epoch for it to converge and to reach the target accuracy. But as we can see from the graphs here, this graph shows the amount of carbon emission versus the number of centralized epoch. We convert all the communications round of federated learning to centralized epoch, so we can plot all the curve in the same graph. For one centralized epoch, it means like the deep learning model go over the entire data set once. So if we have a client pool of 100 and each time we select 10 clients, then 10 communications round equals to 10 communications rounds with one local epoch equal to one centralized epoch. And if we do 5 local epoch, it means that 2 rounds equal to 1 centralized epoch. As we can see here, the gradients of the centralized learning is much higher than the federated learning, which mainly because the GPU has much higher power consumptions than the edge device like TX2 and Xavier NX. if we consider V100, it has the theoretical maximum power consumption of 250 watts compared to the TX2, which has only 7.5 watts, and the Xavier NX, which has only 10 watts. So the gradient for the centralized learning is much higher than the federated learning. And the gradient for the federated learning with one local epoch is higher than the 5 local epoch one, is because one local epoch has more communications cost, and the communication cost is actually 5 times than the 5 local epoch ones. So if we do the calculations, it shows that the carbon emissions resulting from the communication take up to 33% for the 5 local epoch of the total carbon emissions, and 75% for the 1 local epoch. And if we go to the next slide, we can see that if we compare federated learning using Fed-Adam aggregation strategies in both IID and non-IID setups, we can see that the carbon emissions is actually much lower than the centralized learning. For IID setups, federated learning emits 42% less compared to centralized learning. And for the non-IID, even we need more communications round for it to reach the target accuracy, it's still 25% less compared to centralized learning. Even if we compare to the more efficient data center with only 1.11 PUE ratio, which is the PUE ratio reported by Google in their data center, the IID setup is still more carbon efficient. And if we go to the next slide, by comparing different aggregation strategies between the more standard federated averaging with more complex Federated strategies, we can see the aggregation strategies played a rather significant role in reducing the overall carbon emission. It reduced the carbon emission by at least 50%, and it reduced even more with 1 local epoch setups, because it reduced the number of the communications round required much larger than the 5 local epoch setups. If we look at this green break-even line in the graph, it shows that if the centralized learning only emits the same amount of carbon as the federated learning using Fed-Adam non-IID 5 local setup, which is the last column, you can only train for 4 epoch, but it needs at least 6 epoch to reach the target accuracy of 60%. And this gives us another perspective how carbon efficient federated learning can be. But if we look at the next case study in CFA 10, carbon footprint of federated learning depends on a lot of different factors, and it can consume a lot more energy, and emit way more carbon than centralized learning if the setup is not ideal. Here we look at the CFA 10 dataset. For this dataset, we choose to use a rather complicated deep learning ResNet 18 model, which has 11 million of parameters to communicate in each round. And we conduct the experiment over a much larger client pool of 500, but only select 10 clients as before. So as we expected, it will need way more communications round for it to reach the target accuracy. Due to the large model, carbon emission take up to 75% of the total emission for 5 local epoch, and 93% of the total carbon emission if we only do 1 local epoch. And this can also be shown in the graphs here. For the graphs, the federated learning with only 1 local epoch, the gradient is actually much higher than the centralized learning, even though the power of the edge device is much lower than the GPUs, which mainly because of the communications cost. Each round, after each round, the communications cost is constant. So with one more round, it will just emit more carbon emissions due to the communications cost. As we show from the table here, even if we compare the IID setups with Fed-Adam strategies, which we consider as more advanced and more efficient, federated learning, it still emits 16 times more carbon than centralized learning. And this difference is much bigger if we consider non-IID setups. If we go to the next slides, the same as the speech command dataset, the non-IID emits more carbon than IID partition, but if we compare the 5 local epoch setups, the difference is as high as 11 times. The larger difference in the experiments mainly because we have much larger client pool, but still only select 10 clients. So it needs way more communications round for it to reach the target accuracy, and the communications cost here is just plays a really significant role and take up a very big percentage of the total carbon emission. So as the same as before, if we look at, go to the next slides, by comparing different aggregation strategies between standard fed averaging with fed add-on, we can see that the fed add-on still reduce the carbon emission by 60%, and it reduced even more if we only do one local epoch. And here in the table, it shows the greater sign here. It means that if we only do one local epoch with non-RID, the fed averaging doesn't reach the target accuracy within 5,000 communications round. So the actual carbon emission is way bigger than this. And if we look at the graph here, we do the break-even line by calculating how much communications around federated learning can do if it only emits the same amount of carbon as the centralized learning. And the result is that it can only be able to train for 21 rounds for 5 local epoch and 27 rounds for one local epoch, but it needs more than at least 350 rounds for these setups for it to reach the accuracy. So the difference here, as we see, is quite big. Through our studies and analysis, we can show that there are a lot of different factors like the federated learning, the carbon emissions can. The different factors like it can impact the carbon emissions of federated learning. Here we would like to quickly go through 3 main points. The first is the physical locations. The physical locations is very intuitive and straightforward. If the conversion rate is small, the carbon emissions will definitely be small in these locations. But the reason we want to mention this point is that federated learning provides the advantage compared to centralized learning, because federated learning can be trained without moving data to centralized data centers. And the data owners nowadays hold more and more sensitive information, and because of that, there are more data privacy legislations like GDPR preventing moving data freely. In this case, even we know that training in certain locations will be more carbon efficient, but we are not. It is possible that we cannot just do that by moving the data into that the data center in that location for training. So it can be very difficult for people to choose freely in the locations where the training happens. But unlike the centralized learning, federated learning provider solutions allows the device to be in all different locations, and it gives us a large potential if we can choose the devices in certain locations for training more than the other locations. And the other 2 points, as we mentioned before, and the second point is that the carbon emission will largely depend on the data distributions. As we can see from the case studies before, the IID setups is generally more carbon efficient than non-IID, mainly because the number of communications round for IID is much less than the non-IID setups. One interesting point to note here is like for the speech command, the non-IID with one local epoch fed averaging is actually lower than the IID setups here. And the reason for that is because the speech command dataset is naturally non-IID. It has 60% of the data in the class unknown, and even we do the IID setups here only means that the distribution of each client's host is the same as the whole data set, but it doesn't really mean that it's IID in the same sense as the CFA data set. And the third point is that carbon footprint depends largely on aggregation strategies, as we show from the 2 case studies before as well. Deploying more advanced strategies such as fed add-on can significantly reduce the number of communications rounds required regardless of the data set and the data distribution. Hence, it can directly impact the carbon footprint as a result. So I will hand over back to Nick for the conclusion.
Sorry about that. So Xinchi just did a wonderful job in providing you this sort of fire hose of important information that our studies and frameworks that we developed have enabled us to discover about how federated learning behaves within the sort of manifold of carbon. And so we find that, there's this interplay of location, the tasks that's required, the architecture, the network, the hardware, the comms. This framework allows you to have analysis over this rich interplay. And so we think this is really just only the beginning, because now we have this framework to analyze the carbon footprint of federated learning. We can then start to take what is actually the the more important step, which is how you can design federated learning methods to become more carbon friendly. And so how do you do client selection, convergence, hyperparameters, all these things we conventionally would study, but done so from a viewpoint of how carbon emissions can be better managed. So I see we're running very low on time. Javier's popped back. So I'll just leave it here and we can take questions from you as to the details of the study, but also where we see federated learning potentially enabling more sustainable machine learning solutions moving forward. So thanks for your time.
Okay, well, thank you, Nick and Xinchi, for the very interesting talk. We have a couple of questions. I think we're running a bit tight in time, but we can take one. One person was asking, was mentioning that some of the data centers from these large companies like Google, they do run on renewable energy. So he or she was pointing out that maybe in those cases, it might be more efficient to the standard data center training. What are your thoughts on that? I guess not all data centers are running on green energy, right? Maybe that's only possible for these large corporations.
Yeah, but so I guess one thing I'd point out is there's not always the opportunity to have a data center running on renewable energy, and when those opportunities are not possible, we're going to need to have methods of having a small carbon footprint, and so that's why we're so interested in being able to do this. And second of all, if as we start to move forward to methods that use unsupervised learning, where you need to use data that's on the edge. Even if your data center is powered by renewable energy, you still are going to need to have that data move from the edge to the data center, which is going to be at an extreme cost as you start to train on lots of unlabeled data that needs to move, and you're not able to centrally collect labeled data in a curated fashion that we have today.
Yeah, good point. Okay, I think we should move on to the next speaker.
Sure.
So thank you, Nick and Xinchi.